Hello everyone, I'm Yuk Zhang from University of Southern California. I'm glad to share our research entitled TriLock IC Protection with Tunable Capability and Resilience to Set and Removal Attacks. First of all, I'd like to thank Professor Nuzo and my advisor, Professor Burrell, for their support, and a special thank you to my co-author, Yinghua Hu, who equally contributed to this work. I'll start with the background and motivation of the work. Then I will illustrate the methodology of TriLock and show the experimental results. Finally, I'll conclude our work. With the increasing complexity of the IC design, the designers tend to focus on the design work and outsource the fabrication to foundries. An IC supply chain is formed with more specialty services involved, such as physical layout, package design, and testing. Although the supply chain provides economic benefits and convenience for the participants, it raises security issues. The intellectual property, for example, the design of the chip, could be reverse engineered, cloned, and overproduced after leaving the design house. Logic locking is one of the most investigated methods to thwart the attacks on the supply chain. Logic locking can be divided into combinational logic locking and sequential logic locking. Combinational logic locking adds configuration to the combinational portion at the gate level or RTL level and requires the correct key to unlock the true functionality. Sequential logic locking, on the other hand, creates new states in the state transition graph and modifies the original transitions. The correct functionality is typically retrieved by providing a key sequence via the primary input ports during the first few clock cycles. Sequential logic locking shows the promise of significantly increasing the attack effort at a reasonable cost by expanding a circuit's state space. However, the fast-growing attacks keep challenging the locking methods. A robust sequential locking scheme that can offer quantifiable protection is still elusive. So in this work, we focus on sequential logic locking. There are three metrics to evaluate a sequential logic locking scheme: the set attack resilience, functional capability, and the removal attack resilience. We summarize the related works in this table. To the best of our knowledge, none of the existing sequential logic locking methods can provide high resilience to both set-based and removal attacks and tunable functional capability simultaneously, which motivates us to develop TriLock. Let's take a look at set attack resilience first. As set-based attack cannot be applied to sequential logic locking methods directly, the set attack resilience we are talking about is the resilience to sequential set-based attacks. Here is a brief review of the sequential set-based attack. Sequential set-based attack assumes that attackers have access to the netlist of the locked circuit and unlimited access to the correct input-output pairs from the original circuit. The first step is to enroll the locked sequential circuit with a specific enrolling count. We use the small letter b to denote this enrolling count. By doing this, attackers can get a combinational circuit that represents the behavior of the locked sequential circuit over the first b clock cycles. Then, attackers formulate an set problem to print out the wrong keys. An iterative key elimination process is executed by searching for distinguishing input patterns, which are also called dips, via set solver. A dip is an input pattern of the locked circuit for which there exist two different keys that lead to different outputs. The number of dips is used to evaluate set attack resilience. The higher the number of dips, the better the set attack resilience. For a combinational circuit, we can use an error table to describe the output of the key input pairs. As an example, this is the error table for a combinational circuit with 3-bit key and 3-bit input. In this table, each column represents a key value and each row represents an input value. The cross means the output of a specific key and input is different from the correct output of the same input. The error table can be further simplified. We use the red grids to represent the crosses. This error table is an example of a low set attack resilience design because each dip could print out multiple incorrect keys, and 2 dips could rule out all the incorrect keys. In contrast, this error table represents a design with high set attack resilience because each dip could rule out only one incorrect key, and all 7 dips are required to get the correct key. The second metric is functional probability. For a combinational circuit locked by an arbitrary logic locking method, the functional probability is the ratio of the number of corrupted output and the number of the input key combinations. We define the functional probability over the unrolling depths for a sequential circuit locked by a sequential logic locking method. A high functional probability indicates that a random key input pair will produce an error with high probability, so higher functional probability is desired. Here is the functional probability for the previous examples. In the case of low set attack resilience, the functional probability is 0.36, while the functional probability is 0.11 for the error table of high set attack resilience. Typically, there is a trade-off between set attack resilience and high functional probability. The third metric is the resilience to removal attack. Sequential logic locking usually requires adding extra state registers. In the removal attacks, the first step is to distinguish the extra registers from the original registers. Attackers can leverage a strongly connected component algorithm known as the SCC algorithm to cluster the registers on the register connection graph. Then, attackers may remove the locking logic related to the extra registers. To evaluate the removal attack resilience, we can apply the SCC algorithm on the register connection graph of the locked netlist and check the property of the resulting SCCs. Based on whether an SCC contains only the original registers, only the extra registers, or a mix of both, we denote an SCC as an original SCC, extra SCC, or mixed SCC, respectively. The high removal attack resilience expects fewer original SCCs and extra SCCs. In this figure, the extra SCC and original SCC can be distinguished, so the removal attack resilience is not good in this case. In contrast, there is only one mixed SCC in the red figure, which means the extra registers and the original registers cannot be distinguished by SCC algorithm, so the removal attack resilience here is good. As an overview, TriLock is a sequential logic locking method featured set attack resilience, tunable functional probability, and removal attack resilience. We proposed an error engineering technique to break the trade-off between set attack resilience and functional probability, and a state encoding technique to improve the removal attack resilience. The figure here shows the encryption flow of TriLock. We compute the configuration parameters of TriLock based on the user-required security level and modify the original circuit accordingly. Then, we use state encoding method to improve the removal attack resilience. To achieve set attack resilience, we adopt a point function to configure the output error distributions at each unrolling depth. Here is an example of the error table for 2-input circuit with 2 of the key sequence length and 2 of the unrolling count. The point function guarantees that each dip can only print out one incorrect key. As a result, the number of dips equals the number of wrong keys. As the number of wrong keys increases exponentially with the key sequence length, the set attack resilience also increases exponentially with the key sequence length. From the definition, functional probability at the unrolling depth B can be calculated as this equation. We can see the functional probability decreases sharply with the key sequence length. The right figure visualizes the trade-off between the set attack resilience and functional probability. The blue line represents the number of dips and the black curve shows the functional curability. We leverage the temporal dimension of the sequential logic locking to boost the functional curability without compromising the set attack resilience. We increase the key sequence length and add errors at the new input key pairs. I'm going to use an example to illustrate our method intuitively. In the last example, we achieved 15 dips for a 2-input circuit by setting the key length as 2. The functional curability in this case is 0.059. After increasing the key length by 1, the size of the error table is extended. The red arrows are duplicated to maintain the same number of dips. The extended table provides us a set to add more errors, which is colored in blue. We formally proved in our paper that we can add errors at the blue grade to increase the functional curability without hurting the number of dips, and we can control the number of errors to configure the functional curability. In this example, if we add errors at all blue grades, we can achieve 0.77 of functional curability. The equations of set attack resilience and functional curability are shown here. We provide the mathematical details and proof in our paper. We denote the length of the key sequence used to set attack resilience as kappa s, and the length of the key sequence used to boost functional curability as kappa f. Alpha is used to tune the final value of functional curability by setting the number of the blue arrows. The red figure presents the number of dips versus functional curability. From here, we can see that the functional curability is decorrelated with set attack resilience and can be configured by setting alpha. Our error engineering technique is implemented by adding an error generator and the error handlers to the original circuit. As shown in the figure, the original state registers, which are in blue, and the newly added state registers, which are in green, can be distinguished. This implies that the current encryption is vulnerable to removal attacks. We proposed and implemented a state reencoding technique to increase the removal attack resilience. This technique includes 2 steps. We first select pairs of original and extra registers. Then we insert a state encoder and a state decoder for each pair of registers. In the state register selection, we adopted a greedy method to iteratively select the registers which can merge the most original SECs and extra SECs after being re-encoded. In the second step of state reencoding, we insert a state encoder and a state decoder for each pair of registers. As an example, a state encoder and a state decoder are inserted between the combinational logic and the 2 registers R1 and R2 to merge the SEC containing R1, which is SEC1, and the SEC containing R2, which is SEC2. Here we can assume that SEC1 is an original SEC and SEC2 is an extra SEC. Between the encoder and the decoder, R1 and R2 are replaced by a set of encoded state registers. Suppose RA and RB exist in SEC1 and SEC2 respectively. If the encoder and decoder could build the signal propagation path from S1 to any of the encoded state registers, then to RB, and another path from S2 to any of the encoded state registers, then to RA, the register RA in SEC1 can connect to the register RB in SEC2. This path constructs a bidirectional edge between RA and RB, which merges SEC1 and SEC2 into a mixed SEC. To avoid the encoder-decoder structure affecting the circuit function, the output of the decoder should have the same values as the encoder's input signals. The encoder function and decoder function in TriLock are listed here. We implement the encryption flow of TriLock in Python. We use Synopsys Design Compiler as our synthesis tool and a 45-nanometer NAND gate OpenCL library as the target library. Functional credibility is simulated using Synopsys VCS. The set attack resilience is evaluated via the implementation of FunSet. We select 10 benchmark circuits from ISCAS 89 and ITC 99 to assess the performance of TriLock. This table shows the number of dips and the runtime of FunSet when kappa s ranges from 1 to 3. Recalling that kappa s is the length of the key sequence used to set attack resilience. With the 2-day timeout threshold, 4 experiments terminated successfully. If we check each row, we can see set attack resilience increases exponentially with the encryption parameter kappa s. For the timed out results, which are colored in blue, we show the estimated number of dips and extrapolate the runtime by conservatively assuming a constant ratio between the runtime and number of dips acquired from the finished experiments. From the results, 77% of the experiments are expected to require more than 1 year to finish. This figure reports the simulated functional credibility. Recalling that kappa f is the length of the key sequence used to boost functional credibility, and alpha is the parameter to tune the final value of functional credibility. Our results show that the functional credibility is close to its estimate, with an absolute error within ±0.05. The results prove TriLock's ability to configure functional credibility with high set attack resilience. This table presents the experimental results of the SCC algorithm. S refers to the number of register pairs involved in the state re-encoding. We use capital O, capital E, and capital M to denote the number of original SCCs, the number of extra SCCs, and the number of mixed SCCs, respectively. PM is the percentage of registers that are in mixed SCCs. Recalling that fewer numbers of extra SCCs and original SCCs indicate better removal attack resilience. On average, the numbers of original SCCs and extra SCCs are reduced by 72% and 100% when 10 register pairs are selected for state re-encoding. The reduction becomes 84% and 100% when 30 register pairs are selected. While the state re-encoding may not eliminate the existence of original SCCs or extra SCCs for most cases, PM being close to 100 indicates that most of the registers are clustered in one mixed SCC, which means most of the original and extra registers are densely connected. The table shows PM increases to above 95% from 0 after the state re-encoding is applied. The area, delay, and power overhead of TriLock is presented in this figure. We show the overhead versus kappa s because the other encryption parameters seldom affect the overhead. The overhead is computed as the percentage increase incurred by the locking scheme in the area, delay, and power, respectively. From the result, 6 out of 10 circuits present less than 40% overhead in any of the area, delay, and power dimensions. For 3 benches, the power and area overhead exceed 50% when kappa s is larger than 3. However, these circuits can already achieve reasonably high set attack resilience with 2 of kappa s, where the overhead is less than 40%. Moreover, it is possible to implement TriLock only on the sensitive design portions in the system-on-chip scenarios, making the overhead even smaller. In this presentation, we present our cost-effective sequential logic locking method, TriLock. TriLock can achieve high resilience to set-based attack with high functional capability through our error engineering technique. The state re-encoding technique we proposed can significantly improve the removal attack resilience of TriLock and potentially other sequential logic locking methods. Our future work includes investigating other attack vectors to further improve the robustness of TriLock. Thanks for your attention to our work. Please feel free to contact us if you have any questions.